Hello, welcome to the Introductory Physics Lab 1 Constant Velocity, where a instruction was given to create a movie where we can observe a motion of an object in constant velocity to which a comparison can be made of the same type of motion but being predicted by a computer model which governs the equations of constant velocity motion stated in Newton's second law. For this purpose, I've used a tennis ball with a diameter of 0.067 meters with a weight of 0.056 kilograms, both in SI units. The video was shot in MP4 format, 720p, with a frame rate of 30 frames per second, which gives a time between successive frames of 0.33 seconds. I've chosen the plus X direction to point to the right because it is also the direction of the movement of the ball in the video. As you can see here, the ball moves to the right, the successive locations per successive frame is being shown, the graph is plotted, which shows the location as a function of time. The initial time of the program was 0 seconds and the final time was 0.629 seconds. We had to compute a initial velocity, which is the displacement along the plus x divided by the change in time, which gives us a speed of 0.75 meters per second. You can see the equation here. Vector v is delta vector r, the displacement vector divided by delta t, which is 0.025 divided by 0.033, which of course gives 0.75. For the program, we had to insert some values and create a code. The mass of the ball is 0.056 kilograms SI units. The initial position of the ball in vectorial component form is 0 along the x, 0 along the y, 0 along the z-axis. The initial position of the initial velocity vector of the ball in component form is 0.75 meters per second along the x, 0 along the y, 0 along the z. The delta time, which is being iterated here, is 0.01 seconds. So we had to apply a net force in vectorial component form is 0 along the x, 0 along the y, 0 along the z. This has to be 0 because it is a constant velocity motion, so the net force acting on a object in such a motion is always 0. We had to predict a new velocity each time delta t progresses to the end final time, 0.629, which is the velocity of the ball. It is the current velocity of the ball plus the net force divided by the mass of the ball times delta t. We know that this is 0, so this whole term is 0, which gives us the velocity of the ball is and stays the initial velocity of the ball. This is governed by Newton's second law, also called the momentum principle. Here we had to calculate a new position of the ball each time the frame progresses. So it is the final position is the initial position plus the ball velocity times delta t. We had to print the ball in each successive frame. You can see if as the program runs, you can see the ball moving along the plus x direction, the graph being plotted, location along the y, x along the z, which gives location as a function of time. The results of those two curves, the observed location over time and the predicted location over time, were put in one single graph using Google Sheets. I will show the results here, where you can see the time along the x, location along the y, with the red being the predicted location by the model, which should be a constant line, and it is a constant line, so the model seems to work. Compared to the observed location by the experiment, you can see, as I stated here, that the observational findings seem to correlate well with the model predictions, but As time progresses, as time goes further along the x-axis, there seems to be an increase in disagreement between the location of the model predictions and the actual observed locations. This increased disagreement must be due to a force we are missing or ignoring, which applies a net force to our system that is not included in the model calculations for constant velocity, since that's always zero. This discrepancy is most probably caused by friction, which is a contact between the ball and the table, which is probably modulated by the grooves of the tennis ball and the fiber coating, which means if you had a perfect sphere, there would be less friction. To a lesser extent, drag is also a factor because there's contact with the air, which also makes the ball slow down. But this might be negligible since the velocity is possibly not big enough to be greatly modulated by the drag forces. But if we should conduct this experiment in a vacuum of space, far from the influences of gravity and drag and friction, the model predictions and the observations of our experiment would probably be in perfectly consistency with each other. This is it for our Lab 1, constant velocity. Thank you very much.